So here I'm going to talk about how to understand regression coefficients and regression output. I talk elsewhere about how these numbers are generated in the formulas, especially for coefficients and standard errors and R squared. Here I'm really going to show how to interpret the regression coefficients in a table. And basically the idea is that we're testing the hypothesis of the coefficients that we generate are, the null is that there's not significantly different from zero. So if the coefficients are large enough, that means that we could say that it's actually not zero and there's some sort of positive or negative relationship. Okay, and so we'll look at the numbers we get and see how they're related, and then we'll talk about how we can interpret that and test that hypothesis, right? So what I always do is I generate some random data. All right, so I set my seed. I've got random values of x, normally distributed, and the default without any parameters is mean of 0, standard deviation of 1. I'm going to make y and z. This is basically y is going to be 12x, but I've got enough random error in there that it's going to be going to give us an estimate that's not actually 12. All right, but it is related, and we're going to see that our output will show that y and x have a statistical relationship. Now, z is not related at all. This is normally distributed, but it's not connected to x, but has a mean of 5, standard deviation of 2. But it's an independent variable, and the output will show that it's not related. Okay, so now I'm going to run a regression. I've got my 3 variables. I'm going to make y a function of x and z, so this is like a multiple regression. I'm using the linear model. Y is a function of x and z, and I call it reg. And if you look at my summary here, I have basically this is the output that it gives. Okay, and so if you know how to interpret that, that's what we're actually talking about. Now, the thing we're going to look at is this table here, and then the R squared is actually really, really low. All right, it's super low actually, but that's because I put a lot of variation in the data. All right, so if you look here, I've got coefficients. Right, and so I'm going to look at mostly x and z. The x is close to 12. It's not exactly 12. It's because of that random error. All right, now if you want to test the hypothesis, right, that this is not 0, what you do is you normalize it by the standard error. Okay, so you basically take the estimate minus 0, and then you divide by the standard error. So it's like roughly 3, right? So this t-value is literally the estimate divided by the standard error. And what it's basically saying is how many standard errors is this estimate from 0? Okay, so this is 12, but it is about 3 standard errors away from 0. Okay, and then you could say, well, on the probability distribution, there's really not a whole lot of distribution left, and so you're in the improbable area, and then the stars will tell you that it is significant. And in this case, it's significant at 1%, so it gets 2 stars. Now, z, as I said, is not related at all. If you look, the estimate is 1, you say, well, that's not 0. Well, actually, there's so much error in the data, right, that's quite possible that it could be 0. Okay, so this could be a random error. If you actually divide these two, you pick 1.45 divided by 2, you get 0.7. That is not below the threshold. And if you took statistics, you know the threshold is about 1.95 at 5%. All right, so this is nowhere near the statistical error. So this is the output, right? So these are all related because this is the estimate. This is like remember y was 12x. This is close to 12. But this is the standard error. This is the variation of the data. Dividing these two gives you the t-value, and then if you look where 3 is on the probability, this will be here. And I'll show you that as we go. All right, so this is all related. If you look at a regression table, you make a regression table, you pick one of these 3, only one, you put it in parentheses, and then you, of course, leave a note to the reader saying which one you picked. Because if this were your, let's look at this one. If none of these are pretty good, but if you say this is your standard error and you put in parentheses, people might think it's a t-value. And then people would say, oh, that's significant because a t is above 2. But a standard error makes it not significant, so you absolutely have to tell your reader. All right? So I'm going to make a coefficient table, and then what I'm doing is I'm taking elements from it. I've got beta for x, beta for z, s for standard error for x and z. I'm going to use that, and basically pulling just those first 2 columns for x and z. Okay? Now, this is the visualization. I was talking about distributions. Here's how it looks. All right, so I'm basically here, I'm just making my x-axis. I'm going to plot a t-distribution for you. Degrees of freedom. Okay, this is actually from the regression. The number is actually 997, but rather than type in 997, I'm going to actually just get it here. And if you look, watch, take df. It's just pulling it from the thing. So if I run a different regression, I won't have to retype it. Okay, now I'm making my y, and this dt is the distribution at every point. So this is just a bunch of points from 0 to from -4 to 4, and then this is plotting the distribution at each. All right, and we'll look at that. So I'm just making a way to plot the distribution. Q5, that's my threshold. I'm going to do everything at 5%. All right, so the cutoff is 1.962. So the t-distribution with 997 degrees of freedom is essentially normal. So this is sometimes we round to 2, but this is the 1.96. Right, you need a t-statistic of 1.96 to be significant. You have to be far enough from 0, okay, to say that you can reject the idea or the null that nothing has happened. Okay, so this is the plot. All right, and so I made the x-axis from 0 to 4, and then I made the y-axis using the df. All right, degrees of freedom, and then dt here is the density of a t-distribution. Okay, now these lines are the cutoffs, and so this is a 1.96, the negative 1.96, and positive 1.96. Basically, if you get a low statistic, right, it could be anything, you normalize it. Actually, you're not using a normal distribution, but we use the word normalizing. Just divide it by the standard error to say how many units is it from 0. Okay, and it has to be more than 1.96 because this is the probability. So remember hypothesis testing, right? It's very common, high probability to be close to 0 or just to be average, right? And then even things that are a little below or a little above average are fairly common too. But only out here are the low probability events. And now you can say, look, my number was so large that it's more than 2 away from 0. And because it's so large, it can't be attributed to chance. It has to be some low probability event that it couldn't have happened by chance. So that's so large that it's improbable. You can reject the null that nothing has happened. You can say that something is there. Same thing for negative. You could be significantly negative too. All right. So what I'm doing here is I'm going to take, this is the normalized coefficient. This is the beta over standard error. I'm going to make it red. All right. So the t-statistic was about 3. In other words, the number I got was so large that I could say that it cannot be attributed to chance. This is a significantly positive coefficient. And I made the data that way, and that's how they turn out. All right? And what you're basically doing is you're testing this. This is my coefficient, right? My number was normalized to be 3 units, right? And here's my 3. Okay, so it's beta, and we're testing that it's different from 0, so we're subtracting 0, and then dividing by the standard error. Now here's the t-value by hand, the p-value by hand. All right, and so pt, right, we did dt, this is pt, gives you the probability for this specific number with this specific degrees of freedom that matches what the table had, right? And so this is the coefficients we had to show first. We did the estimate, standard error, we had the t-statistic here and the probability, we kind of regenerated these by hand, okay? Now, that's x. I made x so that it is significant. Now, z is not significant. Remember, I just made random data. Okay, so here we plot the numbers again. Here's my thresholds, and here's my new statistic, right? And so when we did it, we said it was 0.7, all right? This is not a large enough number. You could say, well, I thought the number was 1, but actually it is only 0.7 t units away from 0. Okay, so it's not large enough to not be improbable. Okay, you could say, well, this is the probability of outcomes. This kind of falls within the typical range. This number's typical, it's not significant. Therefore, we reject the null, all right, and we say that we reject the null and say that this is not any different from 0. All right, and so the p-value, remember, that it has to be 0.05. This is way too large because there's like literally 24% on each side, 48% outside. This is not a very uncommon occurrence, all right? So here's our results again. You say, well, the estimate was 1.446. I thought this is not 0, but there's so much variation in the data that this could just happen on its own, all right? And now, so the t-value is 0.7. It is not above 2. And so these are all related, right? Divide these first columns to get the t-value, and then you say, well, 7 is not here. And if you look at the probability of above and below on both positive and negative, there's actually 48% of the curve, all right, is on the other side of it. So it's basically in the middle, right? It's basically in the middle 50%. It's not different from 0. Now, economists tend not to do confidence intervals, but some software puts it out. I make these bands, all right, so this is my 1.96, All right, and then basically I'm adding 2 standard errors on each side. I just made a little table here. These are the 95% confidence bands, and you can see that the 95% confidence interval goes from 4.5 to 20.8. This never crosses 0. You can say that the confidence interval does not cross 0. It's always positive, therefore the coefficient is positive. Okay, but if you look at Z, it does cross 0. So you can say, look, that confidence interval could be negative, it could be 0, it could be positive. There's no evidence that this is not 0. Okay, and just to reiterate, when you look at an econometric equation, an OLS coefficient, you're basically testing whether it is 0 or not. Okay, that the effect of a variable is positive or negative. Okay, if it crosses 0, then you can't reject the idea that it has no effect at all. Okay, so X doesn't cross 0, so it's significantly positive. Z does, so it's insignificant. Okay, and then that's where the table comes from. So we've got our coefficient X close to 12, significantly positive. Z, the coefficient is positive, but it's insignificant. All right, and like I said, R squared is really, really low. Okay, so we look at mostly the coefficients and R squared, but everything else, I say in other classes, never gets put in that regression table, right? This F statistic doesn't show up. That's a joint test for all coefficients, okay? Now, as one final test, I say well, I know I programmed it to be 12. Well, can I prove that it's significantly different from 12? So here's 12.693. All right, what if I subtract minus 12? All right, so this is the only difference from 12. Is that significant? And it's so close to 12, the standard error is so large that this p-value is huge. So there's actually no proof that the number that I generated is not 12. It just could be anywhere from 4.5 to 12.8, or 20.8. All right, so it does cross 12. I can't say that it's not 12. Right? Now here's the final thing. I'm redoing Z, making Z1. This is related to Y. Okay, so it's normal. I've made 1,000 observations. I got a kind of a big standard deviation, but it's related to Z. I'm going to run a new regression with Y as a function of X and my new Z. So is this significant? The answer is they're both significant. The intercept actually is not. Look at the huge p-value. But X, again, is significantly positive. All right, you can see that it's still close to 12 anyway. But the t-value doesn't really change much, but it's still positive. It's above 2. P-value is below 0.05. All right? And again, if somebody just reports the standard error, you just do it in your head. And you say, okay, I'm going to 11.6 divided by 3.74 is about 3. All right? This just does the division for you. Okay? Z1 is significantly negative. So I made it to be negative. You could see up here that this is a negative sign. So this is a negative coefficient. It goes both ways. T-value is extremely huge. We look at the absolute value. It's way above 2 in absolute value. And then finally, you can interpret this. This is just e to the negative 16. This number is a decimal with 16 zeros. And this is as low a number as the software can generate. So this is essentially 0. All right, that's what it is. It's just exponential with negative 16. That's how it reads. 0.000 with 15 more, right? So this is hugely, significantly negative. Just have to understand what this number means, okay? It's just a way of writing the smallest decimal you can get. R squared is a lot higher. Remember, adjusted R squared takes into account the number of variables. It's about 0.19. Not super high in general, but higher than the one before. So you can make a table with this, and I would round it to 3 digits, and I would round one of these. I choose the p-value. Don't show the other ones, and then you would have the R squared and possibly the sample size, which is 1,000 in there, right? But that's how you interpret it. You look at the estimate, standard error, you divide, or you go straight to the t-value and say this is pretty low t-value, and that's directly related to the fact that if you're not far from 0, the t-value is small, p-value is going to be large because there's a lot of distribution left, okay? And it goes both ways as well. So this is also negative, but this is not significant. X and Z1 both are, right? So that's the idea. You're generating output, and you're basically doing this hypothesis test whether one or more of the coefficients are significant. You can use any one of these numbers, but you have to know how to interpret them. Standard error, how many standard errors you are from 0, and then you're looking at how much distribution is left with that p-value. All right. So again, you can look for the theory. I've got some other videos up, but right now we're just interpreting and understanding the regression output and the coefficients.